Calculate annual yield on a bond for varying compounding periods in a year. Pay attention to the learning objective keyword here. We have to calculate. Yield measures, which we have seen, yield to maturity, correct? Yield measures on capital market securities are stated as annualized and compounded. So when we say a bond has a 4% yield to maturity, that is an annualized yield, and it is already a compounded yield. And the yield itself depends on the periodicity. That means the number of interest payments per year. So when we say it's a 4%, this bond is yielding 4%, is that based on an annual coupon, a semi-annual coupon, quarterly coupon, monthly coupon? So let's just see how the yield to maturity changes due to periodicity. Let's say that we have a 5% stated annual rate. And we're just going to change the compounding periods and see what happens to the effective annual yield, the EAY. If interest is paid annually at a 5% stated annual rate, a dollar invested today will grow to $1.05 a year from now. That is 5%. Pretty straightforward. If it's semi-annual, that means we'll get $2.50 every 6 months. So we can compound that in 1 year. Our future value will be 105.0625 or 5.0625% effective annual yield. If we compound more frequently, look what happens. The yield increases until we get to continuous compounding. That is E. Whenever we continuous compound, it is E to the RT, T expressed in years because it's 1 year. The T is 1, so just E to the R. 5.1271. What happens if we have a zero coupon bond? It has no coupons. So if we say, well, what's the periodicity of a zero coupon bond? It would be arbitrary, but we can use different periodicities to compare. We can say, well, we can invest in a 5-year semi-annual bond or a 5-year zero coupon bond, which has the higher yield. We could just assume the 5-year zero coupon bond has a semi-annual compounding and just discount it at a semi-annual rate as opposed to an annual rate. So let's say we have a 5-year zero coupon bond at 80, and we're going to try different periodicities here. So annual, it's just discounting at R for the 5 because it's a 5-year bond. So we just solve for R. You just rearrange this, solve for R. You'll get to 4.564. And notice what happens with the yield here. It drops. Notice the yield here increases the more we compound, but the yield here decreases the more we compound, and it's very easy. Here, we're calculating a future value. So we're discounting at a, whenever you can compound more frequently, your future value ends up being higher. Here, the future value is fixed, and we're calculating a present value. So to get a higher and higher yield, you'd have to get a lower and lower present value, but the present value is also fixed. So what happens is to get from 80 to 100 over 5 years, the more frequently you compound, the lower the rate you need to get there. Let's look at the semi-annual yield, 4.513. This is also referred to as a yield per semi-annual period, also called a semi-annual bond basis yield or a bond equivalent yield. So when we calculate the semi-annual yield, the R we'll get here, we'll get an R over 2. Then we multiply it by 2 to get to 4.513. That's why we say we take the semi-annual per period times 2. That is also referred to as the semi-annual bond basis yield or a bond equivalent yield. So based on the last screen, let's say we're looking at 2 bonds, 5-year bonds. One is stated based on semi-annual compounding. We have a yield to maturity, and the other we have a yield to maturity based on quarterly compounding. Can we compare those 2 yields to maturity? Not really. We have to compare them in the same periodicity. So we have to take the semi-annual yield to maturity and say, well, what is that equivalent to if it were compounded quarterly? And this is what we're going to do here. We're going to convert one bond from a certain periodicity to another to be able to compare them. And this is what the formulation looks like, and it looks rather daunting, right? So it's easier to show you an example. So let's say we have a 3.582% semi-annual bond basis yield. We've calculated the yield on a bond. We get to 3.582%. And we want to compare that with quarterly bonds to see if it has a better yield than a quarterly bond. Well, if that were compounded quarterly and not semi-annually, what would be its yield? So look what we do in the first term. We take the 0.03582, divide by 2, and square it. So all we're doing is we're saying, well, if we did have something that had a yield of 3.582% with semi-annual compounding, what would $1 grow to? And it would grow to $1.036141. That is this term. And what are we going to do over here? We're going to solve for this this amount in the numerator over here, what the rate is based on quarterly compounding. So let's just, I've done all the algebra for you, but I'll walk through the steps. Notice we have a power of 4. Let's get rid of the power of 4, which means that this side will take the fourth root of this side, but we already know, we can already solve numerically what this is here. We take the fourth root. So that gets rid of the 4 on this side. Well, we have a 1 on this side, so let's subtract the 1 over here. That gets rid of the 1. Well, we are dividing by 4 here. Let's multiply both sides by 4. There we go, to isolate what the rate would be for 4 years. Sorry, for a quarterly compounding. We get to 3.566. So what this is saying is that if we observe a semi-annual bond with a yield of 3.582, and we're comparing it with a quarterly bond, and we find a quarterly bond yielding 3.566, we can't just say, well, the 582 is greater than the 566, so let's buy the semi-annual. Once you convert the semi-annual into quarterly, you would say this rate compounded semi-annually would grow to the same amount that this rate would compounded quarterly. So if we put $1 in each one, we would end up with the same future value. That's why you have to convert the periodicities to compare together. What if it were monthly? Well, this here stays the same. This part here stays the same because we can solve for that. But you'd have a power of 12 on the other side, so we take the 12th root minus 1, and then you multiply it by 12, and we will get 3.5556. Notice what we have here in our rates. 3.582 was the yield quoted semi-annually. That is equivalent to a yield of 3.566 quoted or compounded quarterly, which is the same as a yield of 3.5556 compounded monthly. Notice that it drops the more compounding that you do. Compounding more frequently at a lower rate corresponds to less frequently at a higher rate. All of these will give you the same future value. So if you put $100 into an investment that has that yield compounded at that periodicity, you will have the same future value. You're indifferent between the three of them. So let's say we're comparing two investments. We can buy a 20-year zero coupon bond for $69.43. Or we can buy a 20-year coupon bond. It pays 4% semi-annually for $101.99. And we plan to hold both of them to maturity. Which one will give us the higher yield based on current rates? Remember, the zero coupon bond, the periodicity is arbitrary. Well, we have to compare it with the 20-year 4% semi-annual bond. So let's discount this at a semi-annual rate. Notice it's R over 2 to the power of 40 because 20 years, there are 40 semi-annual periods. And then we just solve for R. That's the only unknown we have. We get 1.833%. And we can solve for the market yield on this one. Our N is 40, payment is 2. Our PV, again, notice the negative. Our future value, we get 1.928. We want the one that offers the highest yield. There we are. It is the 20-year 4% semi-annual bond. Had we discounted this at any other periodicity, whether it be annual or quarterly, it would not be comparable to the 20-year 4% semi. Well, we've seen before how we deal with negative yields when we're converting a negative yielding asset into different periodicities is nothing different. We follow the same procedure we have already. It is worth mentioning in case you come across negative yields and you say, well, what do I do with negative yields? Same thing. So 5-year zero coupon bond selling at 103.72. Annual yield, we know it's our future value over our present value to the power of 1 over t. T is 5 because it's annual. Subtract out the 1. Negative 0.7278. That is the yield. If we did it semi-annually, we do it to the power of 1 over 10 because we have, well, 5 times 2, right? 10 compounding periods minus 1. But this will give us a yield in semi-annual terms. You have to multiply it by 2 to get back to an annualized and compounded yield, right? Negative 0.7291. Monthly, well, 12 months in a year, 5 years. The power term is 1 over 60, and whatever yield we get as a monthly yield, you must multiply by 12. You get negative 0.7303%. And here we begin the next LOS, so let me read it to you so that we are aware of what it is that we're working on. And it is compare, calculate. Careful with that word. When we see calculate, that means we need to pay attention to any formulas we see. Compare, calculate, and interpret yield and yield spread measures for fixed rate bonds. And we do have some terminology here. The first one is street convention. This assumes that the coupon payments that a bond has is made on the scheduled dates. So the yield is quoted assuming payments are made on scheduled dates. Well, that doesn't sound too bad. Isn't that the way it is? What happens if a payment date is December 25th? Nothing's open December 25th. It's Christmas. You'll actually receive your payment on the 26th. And if you're in the UK and Canada, you'll actually get it on the 27th. So you get your payment later. So the street convention yield does not account for weekends and holidays. A true yield will uses actual payment dates. The true yield will never be higher than the street convention yield. Because remember, one of the rules of money is that money sooner is worth more. So if a payment is supposed to happen on a Saturday, we won't actually get it till a Monday. Well, it happens later, so money's got to be worth less. That's why the true yield will never be higher than the street convention yield. And we have something called a government equivalent yield. This is for restating a bond with a day count convention of 3360 to actual. And what we do is we take the yield, that is whatever yield we get with the 3360, and you just multiply it by 365 over 360. Next term, simple yield. Our numerator here is our coupon payment, which is a cash payment we would receive, plus the straight line amortization of premium or discount. So the whole top line is your yield. It is your coupon and the amortization of any premium or discount. So it's your yield over PV flat. This is common quoting yield for Japanese government bonds. Let's move to bonds with embedded options. They can be callable. If they're callable, we may not be able to hold them to maturity. So calculating a yield to maturity might not make any sense. So we calculate a number of yields. A callable bond will typically have a call schedule, 3 or 4 different call dates. That's called a Bermuda call option, when you have 3 or 4 dates on which you can call the bond. Each date will have a different price. So let's just calculate one here. Let's say that we have a 6.5% 7-year semi-annual bond at 106.25. This is 7 years, and we're looking at our call schedule at the end of year 3, year 4, year 5, year 6, and year 7. So it's not callable for 3 years. In case you're wondering, how could it possibly be selling for 106.25? It has a call blockout period of 3 years. So it's callable at the end of year 3 for 103.25. Callable at the end of year 4 for 102.50, the end of year 5 for 101.75, the end of year 6 for 100, and if it's not called, it simply just matures at par at the end of year 7. And let's calculate a yield for each of these. It's fairly simple. If it's called at the end of year 3, this is really just a 3-year bond. So our N is 6. What's our future value going to be? Not 100. It'll be called at 103.25. Payment is 3.25 because it's a 6.5% semi. And PV is what we pay now, 106.25. We get 5.1496%. That is referred to as yield to first call. We do the same thing for the second call at the end of year 4. This is yield to second call. Look what changes here. If it's called at the end of year 2, then it was a 4-year bond. Sorry, not at the end of year 2. It was called at the end of year 4. In other words, the second call called at the end of year 4, that means it was a 4-year bond. So N equals 8. And our future value is the call price, 102.5. Payment and PV stay the same. There's our yield to second call. I think you can figure out yield to third call. There is call number 3 at the end of year 5. That means it was just a 5-year bond. Our N is 10. It'll get called at 101.75. There's our future value. The rest stay the same. There you go. You could do yield to fourth call. And the final one is yield to maturity. On the maturity date, there's no, it matures. You don't need a call on the maturity date. It's implied. It just matures. And there's your yield to maturity. Of all the yields, a callable bond is often quoted as yield to worst, as opposed to giving you yield to first, yield to second, yield to third. You simply just refer to the yield to worst. So we look at all the yields and we find the lowest one, and there it is right there, 5.1496. So this callable bond would be quoted at a yield to worst of 5.1496. Which just happens to correspond with the first call. Now, we did this very naively, just using our time value of money keys. We would not do that. If we were calculating all of the yields, we need an option pricing model. And to get an option adjusted price, it's hard to explain right now. You'll see this at level 2 when we start using something called a binomial option pricing model, which uses a lattice model to price out options, that if we have a feeling that there is going to be a call at the end of year 3, we would have different prices in the matrix. And then that would result in a different, some different pricing all the way through. So we would be using some kind of option pricing model. Don't worry too much about it right now. In fact, you probably didn't even need to see me draw that out. It's just if you read that line, a more precise way uses an option pricing model to get an option adjusted price, and you're wondering, well, what does that mean? Don't worry, just put a pin in that. You're going to see more than you want to see at level 2 about that. Okay, let's get into credit risky bonds. When we're talking about the yield on credit risky bonds, there is 2 components of it, a benchmark component and the spread. The benchmark component is referred to as the risk-free rate of return. We can typically proxy that with some government risk-free rate. And then you have a premium above that. And since we're taking on risk, it's called a risk premium. This is risk-free. This is the risky part of it. This is the premium we get above the risk-free rate, hence the term risk premium. A risk-free rate of return is a nominal rate, and we know that nominal rates are made up of a real rate plus some expected inflation. So you have the expected real rate, the expected inflation rate, and the risk premium is made up of a premium for differences in taxation, differences in liquidity, and differences in credit risk. Typically, just for ease of working with credit risky bonds, we assume the entire risk premium is attributable to credit risk, even though there is something in there for taxation and liquidity. Rather than attempt to pull that apart, we just attribute the entire spread to credit risk. And as far as the influences on these, macroeconomic factors will affect the benchmark yields, general economic growth, business cycle, fiscal and monetary policy, while microeconomic factors, that means firm level factors or either issuer or issue level factors, will affect the spread. Macroeconomic factors can also affect credit risk as well. That if the economy is in a low growth mode or a negative growth mode, it makes credit bonds riskier, even if nothing changes with the company, but economic conditions change, that credit spread could widen because of macroeconomic factors. The benchmark yield there isn't just one benchmark yield for all risky bonds. It varies across financial markets. Some economies just have more general risk in their macroeconomic environment than other economies do, such as emerging market versus developed market. Fixed rate bonds often use the government benchmark security, which is the most recently issued on-the-run security. So when we're looking at, well, what is a good proxy for the risk-free rate, it is typically the most recently issued benchmark security of the same maturity. So we wouldn't use a recently issued 2-year government bond yield to compare against a 10-year corporate bond. We would use the 10-year government bond yield. This reading here is focusing on fixed rate bonds, yield and spread measures for fixed rate bonds, but the reading does make a note here that says if you have a floating rate bond, rather than the benchmark rate being an on-the-run security, it's typically an interbank rate, which we now use SOFR. We used to use something called LIBOR, but that is dead and gone now. We use a secured overnight funding rate, which is a market reference rate. So we know a corporate bond has a yield that is broken up into a benchmark rate and a spread. And there are different ways of measuring that spread. So we're going to do a couple on this screen. We're going to look at a G spread, an I spread, and a Z spread.